Right now, somewhere in your car or in the electric vehicle parked outside your window, there is a 1,000-pound problem. Not a flat tire, not a failing engine, a battery. It's the single heaviest part of every EV on the road. It does one job. It stores energy. Then it just sits there, adding weight, wasting space, killing range. But what if the battery wasn't in the car? What if the car itself was the battery? What if the doors stored electricity, the roof, the trunk lid, the frame itself? What if, by the time you finished watching this video, scientists had already built the first cars whose own bodies act as one giant hidden battery? They have, and what they've created has a name that sounds like science fiction: massless energy storage. This is structural composites, and it might be the most important breakthrough in electric vehicles that you have never heard of. Today, we're cracking open the science that could let an electric SUV drive 70% farther on a battery that, in effect, weighs nothing. Let's start with the brutal math. The average EV battery pack weighs anywhere from 1,000 to 2,000 pounds. That's a baby grand piano sitting in your floor. A Tesla Model S battery, roughly 1,200 pounds. The Hummer EV's battery, over 2,900. That single component weighs more than an entire Honda Civic. And here's the cruel irony of physics. The more battery you add to extend the range, the more weight you have to push around, which drains the battery faster. It's a snake eating its own tail. Engineers have a name for this. They call it the battery weight paradox. Add 100 pounds of battery and you spend a chunk of that new energy just hauling the new weight around. This is why your typical EV, even with a battery pack that costs more than some entire gas-powered cars, still tops out at around 250 to 350 miles of real-world range. The solution can't be more battery. We need a fundamentally different kind of battery, one that doesn't add weight at all. And so we arrive at the most counterintuitive idea in modern engineering. What if the battery wasn't a thing in the car? What if every load-bearing surface, every panel, every beam, every plate of carbon fiber was itself the battery? That's structural composites, and the principle is actually simple, even if the execution is borderline magic. Think about an airplane wing. For decades, engineers stored fuel inside the wing instead of in a separate tank. One part, two jobs: lighter aircraft, longer flight, more range. Now imagine doing that with a battery in a car. The roof of your Tesla isn't a roof, it's a battery shaped like a roof. The trunk lid isn't a trunk lid, it's a battery shaped like a trunk lid. The whole car becomes a giant distributed energy bank, one that holds itself together while it powers itself forward. Engineers call this massless energy storage because the battery's mass is already there. It's the structure. So, in effect, the battery weighs nothing. Let's start with the brutal math. The average EV battery pack weighs anywhere from 1,000 to 2,000 pounds. That's a baby grand piano sitting in your floor. A Tesla Model S battery, roughly 1,200 pounds. The Hummer EV's battery, over 2,900. That single component weighs more than an entire Honda Civic. And here's the cruel irony of physics. The more battery you add to extend the range, the more weight you have to push around, which drains the battery faster. It's a snake eating its own tail. Engineers have a name for this. They call it the battery weight paradox. Add 100 pounds of battery and you spend a chunk of that new energy just hauling the new weight around. This is why your typical EV, even with a battery pack that costs more than some entire gas-powered cars, still tops out at around 250 to 350 miles of real-world range. The solution can't be more battery. We need a fundamentally different kind of battery, one that doesn't add weight at all. And so we arrive at the most counterintuitive idea in modern engineering. What if the battery wasn't a thing inside the car? What if every load-bearing surface, every panel, every beam, every plate of carbon fiber was itself the battery? That's structural battery composites, and the principle is actually simple, even if the execution is borderline magic. Think about an airplane wing. For decades, engineers stored fuel inside the wing instead of in a separate tank. One part, two jobs: lighter aircraft, longer flight, more range. Now imagine doing that with a battery in a car. The roof of your Tesla isn't a roof, it's a battery shaped like a roof. The trunk lid isn't a trunk lid, it's a battery shaped like a trunk lid. The whole car becomes a giant distributed energy bank, one that holds itself together while it powers itself forward. Engineers call this massless energy storage because the battery's mass is already there. It's the structure. So in effect, the battery weighs nothing. The team that's gone the furthest is at Chalmers University of Technology in Sweden. Led by a professor named Leif Asp, this group has spent over a decade trying to build something most engineers thought was impossible. Their secret? Carbon fiber. Yes, the same carbon fiber that makes Formula One cars rigid, the same stuff in fighter jets, racing bicycles, the latest aerospace structures. It turns out carbon fiber has a hidden talent. Beyond being 5 times stiffer than steel at a fraction of the weight, carbon fiber can also store lithium ions. And lithium ions are the heart of every modern battery. So Asp's team did something audacious. They took carbon fiber sheets and used them as the actual electrodes of a battery. The negative electrode, carbon fiber. The positive electrode, carbon fiber coated with lithium iron phosphate. Between them, a glass fiber separator soaked in a special structural electrolyte, a gel that can transport ions while still acting like a rigid composite resin. The result is one single material doing 2 jobs at once. It carries the structural load of a vehicle and it stores electrical energy, like a human skeleton, bones that hold you up while also producing blood. In their 2024 paper in Advanced Materials, the team reported the strongest energy-storing carbon fiber composite ever made, 30 watt-hours per kilogram with a stiffness of 25 gigapascals. That's roughly as stiff as aluminum. Now, you might say, 30 watt-hours per kilogram? That's only a quarter of a normal lithium-ion battery. True, but here's the catch. It weighs nothing extra. It's already part of the car. The mass would be there anyway. And when engineers run the numbers, the implications are staggering. In an electric car, replacing structural panels with structural batteries could increase driving range by up to 70% on a single charge. A laptop could be cut to half its weight. A smartphone could be made as thin as a credit card. And on aircraft, where every pound saved translates directly into longer range or more payload, it could rewrite the rules of electric flight. This isn't a small upgrade. This is the kind of breakthrough that, once it scales, doesn't just improve electric vehicles, it changes what an electric vehicle is. You might be thinking, okay, cool research, but is anyone actually building this? Yes, they are, and one of them might be parked in your driveway. Tesla unveiled its first structural battery pack with the Model Y back in 2021. Now, this isn't the carbon fiber composite from Chalmers. Tesla uses a honeycomb of 4680 battery cells bonded together to form a rigid floor pan that links the front and rear underbody. Same principle, different materials. The battery is the structure. The result? Around 10% less weight and an estimated 14% gain in range for the Model Y. Other automakers are racing to follow. Volvo partnering with Northvolt, BMW partnering with One, General Motors partnering with LG. Even battery giants like CATL and BYD are developing their own structural cell-to-pack designs. But the real prize is the carbon fiber version, the actual massless battery. Volvo is working with Chalmers on prototype trunk lids that can power the trunk light. Aerospace giants like Airbus and NASA are exploring fuselage panels and wing skins that store the electricity to power the plane itself. Drone manufacturers are already integrating structural batteries directly into the airframe, projected to extend flight times by nearly 25%. And one day, even smartphones. Imagine your phone's housing being the battery itself. No more bulky pouch cells inside. The whole device, top to bottom, storing energy. But here's the truth. This technology isn't on the road tomorrow. There are real, serious challenges. First, energy density. Lithium-ion batteries today store about 30 watt-hours per kilogram. The best lithium-ion cells store around 250. That's a big gap. ASP's team thinks they can hit 75 watt-hours per kilogram in the next few years by switching to lithium foils on the negative electrode. That would put them in genuinely competitive territory. Second, safety. Lithium-ion batteries can already catch fire. Now imagine your door panel catching fire. A structural battery has to be impossibly safe, and it has to be safe in a crash where a battery is being deformed and torn apart in real time. That's a regulatory minefield. The world doesn't yet have safety standards for vehicle bodies that double as power sources. Third, cost. Carbon fiber is not cheap. Specialized structural electrolytes are not cheap. The first cars to get this technology probably won't be your everyday Toyota Corolla. They'll be high-end EVs, performance vehicles, and aircraft. And fourth, manufacturing. Building a curved car panel that's also a working battery? That requires a level of precision the industry has never had to deliver before. ASP's team has spun off a startup called Synos to commercialize the tech, but mass production is still years away. Still, the vision is undeniable. Market analysts expect structural battery composites to grow into a billion-dollar industry within the next decade. The first commercial applications are likely in consumer electronics, laptops with shells that double as batteries, drones that fly twice as long. Then will come premium electric vehicles and aerospace, and then, eventually, mass-market cars. When that happens, the modern vehicle will be unrecognizable. Imagine an electric SUV with no separate battery pack at all, just an integrated body of energy. No giant slab of cells under the floor, no range anxiety, no 1,000-pound block of deadweight to drag around. The car of 2040 might look exactly like the car of today, but under the surface, in every panel, every joint, every beam, it's all battery. The structure is the energy. For over 200 years, batteries have been bricks, heavy, dumb, bolted onto things. Now, for the first time in history, we're learning to build energy directly into the bones of the world. It's the difference between a backpack full of fuel and a body that runs on its own. If structural battery composites work, and the data says they will, the future of transport won't be about adding more battery. It'll be about building things that don't need a separate battery at all. The lightest car, the longest range plane, the thinnest phone, all hidden inside the materials around us, massless and inevitable. If you found this fascinating, hit subscribe. Cipher Sci breaks down the cutting-edge science that's changing the world every week. Drop a comment with what you'd want to see store energy first: your phone, your laptop, your car. See you in the next one.